So now let's talk about the fundamental theorem of calculus. It's a very simple statement. In fact, it says the following: that if f is a continuous function on a closed interval from a to b, and capital F is an antiderivative of f on the interval from a to b, then the antiderivative of the definite integral from a to b of f of x dx is equal to the antiderivative at b minus the antiderivative at a. Now, this seems like a very innocuous, simple little statement right here, but we definitely do need to prove this one. And it's important to remember where we've been. We've been talking about taking a Riemann integral, that is, a sum of this function, uh, of a partition under this function from a to b, and we've been saying that the area would occur if we took the norm of these partitions and allowed that to go to 0, which is the same thing as saying allowing the number of rectangles to increase towards infinity, and take that summation to be the area of the region underneath. But how are we connecting that to our antiderivative? And that's the important part that we have to discuss right here. So the first things that we have to do is to, certainly like we've done with our limits, with our sums in the past, talk about letting our, we have to let our area underneath the curve be divided up into some partitions. So we're going to let delta be a partition. That means that we're dividing up our integral, our area under the curve, into subintervals from A to B. Okay, so we're going to go from A to B just like we've done in the past, right? When we were talking about our sums, we said we're going to divide this up and we're going to call that our partition right here. And we're going to be very specific. We're going to say, let's let x of 0 be the very first point, that's A, and let x of n be our very last point, and we're going to divide it up in such a way that we're going to make sure that x of 1 is less, x of 0 is less than x of 1, and x of 2 is greater than x of 1, and x of 3 is greater than x of 2, and so on down the list. There should be a 3. All the way down to x of n, right? So we've got x of n minus 1, all the way down to x of n. We're saying that x of n, that's b right over here, right? And so if we think about it that way, right, that means we're talking about here's x of 0 at a, here's x of 1, here's x of 2, and we just keep on going down the line until we get down to x of n, right? Here's x of n minus 1 just before b. Of course, b itself is x sub n. All right, so this is our partition. So we're going to start on this end of the function right here and talk about the antiderivative of f at b minus the antiderivative of f at a. And let's work with this partition in dealing with this antiderivative. So the first step is to take antiderivative at b minus the antiderivative at a to be the same as this summation. You'll notice what's happening. We're going to add up pairwise f of x of n minus f of x of n minus 1. So we're taking the antiderivative at x of n minus the antiderivative at n minus 1. And we're going to add to that the antiderivative at x of n minus 1 minus the antiderivative at x of n minus 2. And you'll notice what happens if we were to actually carry this out all the way from rectangle n all the way down to rectangle 1. And one by one, we look at the antiderivatives over to each of these intervals. Of course, negative f of x of n minus 1 plus f of x of n minus 1 drops out. And this is what we call a telescoping series. All of the middle terms just drop right out, leaving us with f of x of n minus f of x of 0. So it's completely equivalent to this statement, f of b minus f of a. Because the endpoints at a and the endpoints at b are x of n and x of 0. All right, so what could we do? Well, we could take all of this and re-express this as a summation if we recognize that in any one rectangle somewhere in this summation right here, that we're going from x of I minus 1 to x of I along each of these rectangles, and we're going to add those up. And so re-expressed using summation notation, this is the sum from I equals 1 to n of each f of x of I minus f of I minus 1, the antiderivative at x of I minus the antiderivative of x of I minus 1, right? So we're going to be summing up all of these rectangles right here. And then you look at this expression right here. We've got f of x of I minus f of x of I minus 1. And doesn't that evoke something really interesting? It does. If it doesn't to you, it does to me. Because it looks a little bit like one of our statements that we call the mean value theorem, right? Remember what the mean value theorem would say? If we had an interval, let's say from x of I minus 1 to x of I, what should happen? Well, there should be some c sub I somewhere in the interval such that the slope of the line tangent to the curve would be equal to the slope of the line secant to the curve through x of I at x of I minus 1, right? The mean value theorem says that there must exist some value c sub I on that interval such that the derivative of ci is equal to f of x of I minus f of x of I minus 1 over the difference of x minus x of I minus 1. And again, that's a very familiar term right there from our mean value theorem. Well, how does that help us? Well, that helps us because we have to remember that capital F is an antiderivative of f by definition, so f prime of x is f of x, and therefore we could certainly say that it's the case that if we define each delta x of I to be equal to x of I minus x of I minus 1, if we rewrite this expression just a little bit, right, we're going to see something that looks like this. F of c sub I times delta x of I equals f of x of I minus 1, or f of x of I, minus the antiderivative at x of I minus 1. And since this is true on this particular one interval, if it's true on every I interval, and therefore the sum of all of these on the left, the sum of all of these terms here on the left from I equals 1 to n will be equal to the sum of all of these terms on the right. But as we stated before, well, this is the equivalent of f of b minus f of a, but what about this guy on the left? Well, we might note that if we were to take an infinite sum of each of these quantities, and we let each delta x of I, that is the norm of our partition, approach 0, we might note that this is indeed the Riemann sum whose limit is equal to the definite integral from a to b of each f of x dx. And that is our proof of our fundamental theorem of calculus. Not too shabby.